Okay, so this is the version of the angular momentum algebra that we will be using. Okay. So let's start with the eigenvector of J3. So J3 acting on alpha of M gives me M times alpha M. So all we know about M is that it has to be a real number because J3 is a permission operator. Now let's see what the J3 value, eigenvalue, what happens to the J3 eigenvalue if I apply J plus on this vector. So let's take J plus and act on this vector. Then ask ourselves, what is going to be the J3 eigenvalue? The J squared eigenvalue is not going to be different because we know that J plus and J minus, which go into making J plus, they commute with J squared, so that this is not going to change. But J plus does not commute with J3, so something interesting is going to happen. So we are interested in finding the J3 eigenvalue of this guy. So how do we do that? Well, we use the fact that things in quantum mechanics are not commutative, but they're associative. So we can write this as J3 J plus alpha M. And this is, we use the commutation relationship. And this is going to give me J plus J3 plus J plus times alpha M. So we are using this first one. And then J3 acting on this guy gives me M. So I get J plus M, and then we have J plus, and then alpha M. But then we can factor out M plus 1, and then we have J plus acting on alpha M. In other words, the effect of J plus on the state alpha M increases its M eigenvalue by 1. Can you see that?
Yes, sir.
So
Though it's a bit confusing.
Well, I mean,
yeah, I'll have to work through the algebra myself.
Yeah, I mean, the algebra, of course, you have to do it yourself. But here, what you're saying is that there's a state and an operator is acting on it. You get the same state back with a number, and therefore, this is the eigenvalue.
Yeah.
Okay? So that means that this state, J plus alpha M, is an eigenstate of J3, whose eigenvalue, M eigenvalue, is M plus 1. And of course, it has to be proportional, and there's some proportionality constant C M plus 1. So we'll figure out what C is, okay? So J plus increases the J's 3 eigenvalue. Because it increases the J3 eigenvalue by 1, J plus has a name. It's called the raising operator. Okay. Now we can do the same thing with J minus. So what happens if J minus acts on A of M? And we can apply J3 on it. And then by the commutation relationship, I will get here J minus J3. And now there's a minus of J minus. Remember, there's a minus sign here. There's a minus sign here. And that's this minus sign. And then that's acting on alpha M. And then J3 acting on this thing gives me J minus M minus J alpha of M. And I can factor out J M minus 1 from here. So I get M minus 1. And then I get J minus acting on alpha M. So that means that J minus acting on a state reduces the J3 eigenvalue by 1. That motivates that, writing j minus alpha of m must be proportional to alpha m minus 1. And let's call this proportionality constant dm minus 1. Okay. And we can call j minus the lowering operator.
So the j plus minus are the ladder operators.
Exactly. So j plus and j minus together are known as the ladder operators, because they move us down the they move the system up and down the ladder of eigenvalues. If you start with, say, the j3 eigenvalue m, you can go up the ladder one step at a time by using j plus, or you can go down the ladder one step at a time using j minus. Okay, these are the possible values of j. We don't know what m is, but we know that by using j plus, you can go in that direction. By using j minus, you can go in that direction. Okay. So recall that we set out to find the finite dimensional representation. That means the Hilbert space will have some finite dimension. Now each vector which has a different eigenvalue must be orthogonal. We have proved that theorem. So we are not going to, I have told you all, you have to think about it a little bit. The j squared eigenvalue is not going to change under the action of j's, j1, j2, and j3, or j plus, j minus, and j3. So let's keep that the same. But the m eigenvalue, if it's m and m prime, then they will be orthogonal. So assuming that they have been normalized, but if m is different from m prime, then it'll be orthogonal. And that's a theorem that we proved before. The other thing is that because we're looking for finite dimensional representation, that means that this ladder must terminate somewhere here or here and here. It has to terminate on both ends, otherwise it'll be an infinite ladder, and then the vector space would be infinite dimensional, and that is not what we assumed. Okay, so we are going to restrict those, that assumption. We're going to use that assumption. Okay, so let me just make a comment quickly. And the comment is, we don't have to vary alpha here, because since j squared commutes with j plus, j minus, and j3, the latter actions on the states won't change the value of alpha. If you have done my group theory course, this is related to Schur's lemma. But if you haven't, don't worry about it. All right. So now, how do we, figure out where this series terminates? See that the action of j plus and j minus is encoded in these proportionality constants. So at some point, these proportionality constants will go to 0, and that will terminate the ladder. Okay, we will find the explicit values of C and D. Okay, so that's what we're going to do next. All right, how do we do this? Well, let's evaluate this bracket. Alpha m plus 1 bra j plus alpha of m. Okay, so this thing, j plus acting on this, gives me c m plus 1, and then I have alpha m plus 1 alpha m plus 1. Okay, so this thing gives me this times this. But of course, these two are the same state, so I just get 1 here. So I get c m plus 1 as a result. But this same thing, I could have written it as, the left-hand side, alpha m plus 1 j plus alpha m, and then written it in a way that is taking the complex conjugate of this thing. And because the j plus dagger is j minus and vice versa, we see that we have a j minus here, right? Remember the definition of Hermitian conjugation? This is exactly the definition of Hermitian conjugation. Now, j minus acting on this thing gives me d m alpha of m here. But if I pull out dm from the bracket, I get dm star. And inside the bracket, I get alpha m, which is a real number, so I don't have to bother with the star. And this is 1. So I have established that Cm plus 1 is equal to dm star. Okay, so the two set of coefficients, C's and D's, they are related by complex conjugation.